All right, we're back with chapter 2, part 1, the chemical basis of life. So the big ideas in this chapter are elements, atoms, and compounds, which I'm going to kind of focus on in this first part. Then we're going to get into chemical bonding, and then we're going to talk about water. So life's chemistry is tied to water, and you kind of need to know a little bit of chemistry so you fully understand bio. If you've had chemistry already, this chapter will be very easy. If you are taking chemistry at the same time, it will help you out. And many of you may be taking chemistry next semester. So again, it will help you out. But life first evolved in water. And so we know when we look for living life on other planets or other places, we need to have water available. All right, your body is made up of 70 to 95% water. So living organisms are composed of matter. Matter is anything that occupies space and has mass or weight. Matter is also composed of chemical elements. An element is a substance that cannot be broken down into any smaller substances. In fact, we have this wonderful, and I have one sitting right here, this wonderful thing called a periodic table, right? So our periodic table, that is full of elements. If it's not on this table, it is not an element, right? So you're not gonna find water up there. Water is a compound. It is made up of elements, hydrogen and oxygen. So there are 92. Now, if you look at your periodic table, you'll see there's more than 92 elements on there. And that is because they are, you could say man-made, right? So only 92 elements exist in nature. So the elements that we're going to be focusing on, so when we look at the body percentage of body weight, that the elements that we find in an organism, we've got oxygen, carbon, hydrogen, nitrogen, calcium. We start getting into the smaller percent. So we get into phosphorus, potassium, sulfur. Some of these have really weird symbols. Like, for instance, Y is potassium, start with a K, and that's kalium. These are based off their Latin names, and that's where we get those letters from. And then we have trace elements that make up a very, very small percentage of your body weight. So a compound is a substance consisting of two or more different elements in a fixed ratio. We know, for example, water is always H2O. Sodium chloride, your table salt, is sodium, 1 atom of sodium to 1 atom of chlorine. So that's our sodium chloride. These are really interesting elements. Sodium is actually very reactive to water and will explode if it is exposed to water. And chlorine is a gas at room temperature, and if you inhale it, it's poisonous, so you will die. So sodium, you stick it in your mouth, explodes. Chlorine, you inhale it, it kills you too. Either way, it's really interesting that we take two very extreme elements that are harmful to humans or any living organism for that matter, and we put them together and we get salt, something we put on our popcorn and french fries. And so chemistry, go figure. So there are about 25 elements that are essential to life. 4 elements make up 96% of the weight in most living organisms. So we're going to focus on oxygen, carbon, hydrogen, and nitrogen. Those are the 4 main elements that we find in our body. So again, trace elements are essential, but are only needed in, that is not minute, it's minute. It's spelled the same way. It's minute quantities, that means small. Some of those trace elements are really kind of important, and we found that, for instance, we need iron. Iron is very important to transporting oxygen around your body. We also know that we need iodine. Iodine is an element that prevents the thyroid from kind of growing out of control and giving you what's called a goiter, which is why you read about iodized salt. Our sodium chloride does not have iodine in it, but potassium iodide does. And so when you're eating your salt, it's called iodized salt. It is a mixture of 2 different types of salts. They stick that potassium iodide in there to help prevent you from getting goiters. There are some concerns that sea salt, because a lot of us are into that Celtic sea salt, may not have enough iodine to prevent this. So you do need to be careful with that. And so again, we talk about nutrition facts. Several chemicals are added to food in order to preserve it. If you're one of those organic, all natural people, you'll notice like when I make my own bread, if I don't eat it fast enough, it will mold very quickly because it doesn't have those preservatives in them that keep them from um, molding, especially now in the humidity. And so there are lots of things that we need to look at when we look at our nutrition labels. 2.3 talks about atoms and what they are made up of. So the smallest functioning unit of matter, like I said, is an atom, but we can break an atom down into even smaller parts. And those parts are called subatomic, sub meaning smaller underneath. So we have 3 subatomic particles. We have protons that are positively charged, electrons that are negatively charged. Think of electricity. Electricity is a flow of electrons, and it is a negative experience if you are electrocuted. All right, so electrons are negative, and neutrons are neutral, right? That's where we get that word neutron from. It's neutral. We find the neutrons and the protons are packed into the nucleus, and the electrons are going to be orbiting that nucleus of the atom. The positive protons in the middle will pull and attract those electrons. And so we have that momentum of the electrons spinning around, and they are attracted, or an electron would fly off, but it's attracted to that proton. And we do have some problems with protons because protons, and you guys know, you've done this with magnets, right? You get 2 magnets the same polarity and they repel, and the opposite they attract. And that's what happens here too. Electrons don't want to be by each other, and they have a lot of space to try to spread out to circle that nucleus. But the protons are packed in the middle. And the problem with that is they want to repel each other. And so we have those neutrons in there, and I refer to them as the peacekeepers. They help keep that nucleus stable. So we can see here, here's an example of my helium. So I have my helium atom. We've got 2 protons, 2 electrons, and 2 neutrons. The mass, or what makes up most of the weight of that atom, is the protons and the neutrons. Electrons are so small, they don't really contribute much to how much it weighs. And so the mass number is always the number of protons and neutrons. So just think about it. It's what's in the middle, what's in the nucleus is the mass number. The atomic number is the number of protons. And the way I always remember it is if you look at your periodic table, and I would highly suggest you printing out a periodic table or getting one. You're definitely gonna need one, okay? So when you look at the boxes inside your periodic table, you'll see there's whole numbers and then there's decimal numbers. The whole numbers are the atomic number. You can't have like a half of a proton, okay? But you can, if you guys ever get on your electronic balances, you know you're not exactly, say 170 pounds, you're 170 point something. And that's the mass or your weight, okay? I don't wanna get into the difference between mass and weight. We're not really going to distinguish between that. If you take physics, you will, and they might talk a little bit about chemistry, but I'm not going to bog you down on those details at this point. Okay. So the atomic mass number is the sum of the protons and the neutrons. The atomic number is just the number of protons, and you need to be able to identify that on your periodic table. So here I have 6 protons in carbon, 6 neutrons, so my mass number is 12. I do have 6 electrons. Now I need to have the protons equal the electrons or I have a charge. So if I have 6 positive charges, I need 6 negative charges, and that's my electrons. So although all atoms of an element have the same atomic number, like if you change the atomic number, you change the number of protons, you change the element. But we do have things called isotopes. Isotopes have the same number of protons, but they have different number of neutrons. And remember, the neutrons add mass. And so sometimes when we add these extra neutrons or take the neutrons out, the nucleus becomes unstable and it gives off other types of particles and radiation. And we're just going to leave it at that. If you get into nuclear chemistry, you'll learn about alpha and gamma and all those different beta particles. But what you just need to know in here is that there are what we call radioactive isotopes. They give off energy as they break down into something stable. So an isotope is an atom that has a different atomic mass due to a different number of neutrons. I always call it like a overweight atom, has too much mass, too many neutrons, and so it's not stable. So here, for example, we generally will say like carbon 12. If you look up carbon on the periodic table, you'll see that its mass is 12. And again, that's where those decimals come in, because that 12.011 is an average of all the isotopes. Okay. So we have carbon 12, which is basically your stable carbon. You have carbon 13 and 14, which are your overweight, your radioactive isotopes. Notice they still have the number of protons, right? Or they wouldn't be carbon anymore, but they have extra neutrons. You may have heard of carbon 14 dating, and that's where we will look at that particular isotope, and we can use that to determine how long ago a fossil or an organism. Usually it's a fossil because we need them to be at least between 10 and 15,000 years before this process is really accurate. Now, what you guys will be using them for, because if you guys are going into the medical profession and maybe you've had some tests with this, is that our cells cannot tell the difference between radioactive carbon, like carbon 12, 13, 14, doesn't know, or iodine. We tend to use iodine as a tracer. There are radioactive isotopes of iodine, and they can put that in your body, and then we can use equipment to get images and to get better pictures of what's going on with particular organs or glands in your body. So I would be sure to read page 21 on your book. It goes into a lot of detail. It talks about different types of tests that we do, especially if you're going into the medical profession. I'm personally not going to ask you to give me the details of a PET scan or something like that. But again, this should be interesting to you because ideally this is why you're taking this class. So in addition to benefits, there are dangers associated with radioactive isotopes. And so some of you guys know, radioactive substances can cause DNA damage. And when we damage DNA, this can cause cancer. And so this again is also going to be they'll talk about cancer and stuff like that on that particular page as well. So that concludes the first part of chapter 2. The next section, we're going to get more into the periodic table. So do try to make sure you have your periodic table ready to go for part 2. All right. Again, as always, if you have questions, go ahead and reach out to me and I will do the best I can to answer those questions. Bye.